Design of machine elements to design of springs. Topic is design of springs. Now today in this video we will discuss about the design procedure for helical springs. Before that, symbols used in helical compression springs. So look at the diagram 3.3. Above one is a free length spring, pitch P, inner diameter D1, main diameter D, outer diameter DO, capital DO. And when the second one is a compressed state. So compressed length is LO, free length is L, and deflection, maximum deflection is Y2, initial deflection is Y1. The corresponding force on Y1 is F1, maximum deflection of Y2 is F2, solid deflection of YS is Fs. So L0 is the free length of the spring, small d is the diameter of spring via. Mean diameter of D, capital D is the mean diameter of coil, capital D0 is outer diameter of coil, capital DI is the inner diameter of coil. Small p is the pitch. So pitch is the distance between two springs at free state. F is a load on the spring for axial force. I is number of active coils. I dash is total number of coils. Tau is permissible shear stress or design shear stress. Y is the deflection of the spring. Capital G is modulus of rigidity. Small c is the spring index. Small k, the wall stress factor or curvature factor. F0 or K0 is stiffness of spring or rate of spring. A, clearance is 25% of maximum deflection. Tau Y is torsional yield shear strength. FOS is the factor of safety. F1 minimum load. F2 is the maximum load. Y2 is the maximum deflection. Y dash is the deflection for that load range. N is the number of additional coils. G is acceleration due to gravity. V is the volume. Small m is mass of the spring. Rho is the mass density of spring. Y1 is the initial deflection or compression. Now design of helical springs. So design procedure for helical compression spring of circular cross section. So first one is the diameter of wire. So to calculate diameter of wire, we should use shear stress tau formula from data book, that's 20.22. That is tau is 8f/dk upon pi d cube. Here k is the wall stress factor, that is 20.23 from the book. 4c minus 1 upon 4c minus 4 plus 0.615 upon c, where small c is d by d. Substituting the values of t and d, we get c. Substituting the values of c, we get the wall stress factor k. So substitute the values of k in the equation 20.22, and for given shear stress and load, we can calculate the small d. So we get the small d is the diameter of wire in mm. Selecting the standard diameter from table 20.12 from the textbook, we get the diameter of wire. Second one, mean diameter of coil. So mean diameter of coil, capital D, is C into small d. Since you know the diameter of wire, small d, into C, we get capital D. Outer diameter of coil DO is T plus D. Inner diameter of coil D1 is DI is D minus T. Third one is number of coils. So for that, we have to use the equation y equals to 8f/dq into I upon 4d4. Equation number 20.29 from the textbook. Y is a deflection given, F is a force given, D we know, small d is diameter of wire, G is voltage rigidity. Therefore, we can calculate the I for the number of coils. Fourth one, free length. Free length L0 should be greater or equal to I plus N into Y by plus A, where A is the 25% of maximum deflection, Y is maximum deflection. If assuming square and ground ends, then number of additional coils N is 2. Fifth one, stiffness or rate of spring, F0 is F by Y. So pitch P is L0 minus 2D upon I. See, this is from the equation from the table 20.14 for the book. For natural frequency of helical springs, when one end is fixed, F is 1 by 2 pi square root of 2F4 upon M. When both ends are fixed, 1 by pi 2F4 upon M. Equation number 20.75 and 20.76. When density of steel wire has to be considered, then volume V equals to pi di 1 by 4 pi d square. Weight is volume into weight density, pi square d square di gamma upon 4, 20.47.